Welcome to the lecture of Renewable Energy System. In today's lecture, we will discuss about the fundamental of photovoltaic system and its working principle. Photovoltaic is a solar system technology that uses the unique property of certain semiconductors to directly convert solar radiation into electricity. Photovoltaic systems use wafers typically made of crystalline silicon that are sensitive to sunlight and produce a small direct current when exposed to light. When these PV cells, also known as solar cells, are combined into larger arrangement which is called modules, they produce an appreciable amount of electrical power with no moving part, noise or emission. A photovoltaic system is a electrical system consisting of a PV module array and other electrical components needed to convert solar energy into electricity usable by loads. A PV system components can be arranged in many ways to design the system for different situations, but the most common configuration is a utility connected system which is found on the commercial and residential building. The utility connected PV system is shown in this diagram. These PV systems may or may not include battery storage. The array is usually mounted on a rooftop or nearby on the ground. Electrical components such as inverters, charge controllers, and disconnectors control and conditions the DC power from the array and either direct it to DC load or convert it to the AC power for use by AC load. Some of these components functions may instead be combined together into one power conditioning unit, which is abbreviated as PCU. As of PVC advantages, electricity supplied by a PV system displays electricity from some other power generating technology. If the alternative is very expensive, such as utility connection to a remote location, then the PV system may save the consumer a great deal of money. However, other advantages and benefits of PV system add value beyond the potential financial saving. Many PV systems owners places high importance on producing clean green energy. Photovoltaics is an environmentally friendly technology that produces energy with no noise or pollution. For some owner, operating PVC system makes a statement about protecting the environment and conserving non-renewable energy sources. Also, PV systems are very flexible and can be adapted to many different applications. The modular nature of PV arrays and other components makes system easy to expand for increased capacity. Since there are no moving parts, PV systems are extremely reliable and last a long time with minimum maintenance. PV systems also offer energy independence. A supplement PV system reduces the consumer vulnerability to utility power outage, and a standalone system eliminates it. Furthermore, sunlight is a renewable energy source that is free and readily available, as conventionally produced electricity is expected to become more expensive and PV system costs are generally decreasing. PV systems can also be used to hedge against future energy rate increase. There are, however, some disadvantages to PV systems that have somewhat limited their use. Currently, the most significant issue is the high initial cost of a PV system compared to prices for competing power generating technology. PV systems also requires large array area to produce a significant amount of power. The available solar radiation resources at a particular location determines the feasibility of producing appreciable amount of power. There is also a lack of knowledge among some groups and in some areas about the potential of solar energy system, particularly photovoltaics. Consumer may not know what type of systems are available or even that a solar energy system could be successful for their application or location. Consumer also wishes to install a PV system may discover that the industry infrastructure in their area is not yet fully developed to support their installation. It may be difficult to find a qualified installer in their area, or their installation may be hindered by limited knowledge of PV system and their requirements among the local utilities and code officials. Many leaders in the PV industries are addressing these issues in an effort to promote PV systems. Public and private organizations are subsidizing PV installation in an effort to offset the additional cost and promote the use of green electrical power. Research institutions and manufacturers are working on new PV technologies to increase the efficiency of cells and modules so that more energy can be produced by smaller arrays or in location with the less favorable solar radiation resources. The working principle of solar cells is based on the photovoltaic effects, that is, the generation of a potential difference at the junction of two different materials in response to electromagnetic radiation. The photovoltaic effect is closely related to the photoelectric effect, where electrons are emitted from a material that has absorbed light with a frequency above a material dependent threshold frequency. In 1905, Albert Einstein understood that this effect can be explained by assuming that the light consists of well-defined energy quanta called photons. The energy of such a photon is given by E is equal to hv, where h is Planck constant and v is the frequency of the light. The photovoltaic effects can be divided into three basic processes. Number one, generation of charge carrier due to the absorption of photon in the material that form a junction. Number two, subsequent separation of the photo-generated charge carrier in the junction. And number three, the collection of the photo-generated charge carrier at the terminal of the junction. Absorption of a photon in a material means that its energy is used to excite an electron from an initial energy level abbreviated as EI to a higher energy level abbreviated as EF. As shown in figure A, photon can only be absorbed if electron energy level EI and EF are present so that their difference equal to the photon energy, that should be equal to HV is equal to EF minus EI. In an ideal semiconductor, electrons can populate energy levels below the so-called valence band edges and above the so-called conduction band edges. Between those bands, no allowed energy state exists, which could be populated by electrons. Hence, this energy difference is called the band gap. If a photon with energy smaller than band gap energy reaches an ideal semiconductor, it will not be absorbed but will traverse the material without interaction. In a real semiconductor, the valence and conduction bands are not flat, but vary dependent on the so-called K factor that describes the crystal momentum of the semiconductor. If the maximum of the valence band and the minimum of the conduction band occur at the same K vector, an electron can be excited from the valence to the conduction band without a change in the crystal momentum. Such a semiconductor is called a direct band gap material. If the electron cannot be excited without changing the crystal momentum, we speak of an indirect band gap material. The absorption coefficient is in an indirect band gap material is much higher than in an indirect band gap material. Thus, the absorber can be much thinner. If an electron is excited from EI to EF, a void is created at EI. This void behaves like a particle with a positive elementary charge and is called a hole. The absorption of a photon therefore leads to the creation of an electron-hole pair. The radioactive energy or the radiative energy of the photon is converted to the chemical energy of the electron-hole pairs. The maximum conversion efficiency from radiative energy to chemical energy is limited by thermodynamics. This thermodynamics limit lies in between 67% for non-concentrated sunlight and 86% for fully concentrated sunlight. Usually, the electron-hole pair will recombine, that is, the electron will fall back to the initial energy level EI. The energy will then be released either as photon radiative recombination or transferred to another electrons or holes. If one wants to use the energy stored in the electrons hole pair for performing work in an external circuit, semi-permeable membranes must be present on both sides of the absorber, such that electrons only can flow out through one membrane and holes only can flow out through the other membranes. In most solar cells, these membranes are formed by N and P type materials. A solar cell has to be designed such that the electrons and holes can reach the membranes before they recombine. That is, the time it requires the charge carrier to reach the membranes must be shorter than their lifetime. This requirement limits the thickness of the absorber. Finally, the charge carriers are extracted from the solar cells with electrical contact so that they can perform work in an external circuit. The chemical energy of the electron-hole pair is finally converted to electrical energy. After the electron passed through the circuit, they will recombine with holes at a metal absorber interface. The two most important loss mechanisms in single band gap solar cells are the inability to convert photon with energies below the band gap to electricity and thermalization of photon energy exceeding the band gap. These two mechanisms alone amount to the loss of about half the incident solar energy in the conversion process. Thus, the maximum energy conversion efficiency of a single junction solar cell is considerably below the thermodynamic limits. The characteristics of a PV cell is typically defined using conventional PN junction diode. The diode characteristic is shown in this diagram. If we were to apply a voltage across the diode terminal, forward current would flow easily through the diode from the P side to the N side. But if we try to send current in the reverse direction, only a very small reverse saturation current will flow. This reverse saturation current is the result of thermally generated carriers with the holes being swept into the P side and the electron into the N side. In the forward direction, the voltage drop across the diode is only a few tenths of a volt. The voltage current characteristic curve for the PN junction diode is described by the following Shockley diode equation, which is written over here, where ID is the diode current in the direction of arrow in amperes. VD is the voltage across the diode terminal from the P side to the N side in volts. I naught is the reverse saturation current in amperes. Q is the electron charges which has the value of 1.602 into 10 to the power minus 19 coulombs. K is the Boltzmann constant which has the value of 1.381 into 10 to the power minus 23 joules per Kelvin, and T is the junction temperature in Kelvin. To understand the voltage and current characteristic of a diode, solve this given exercise using Shockley diode equation. Let us consider what happens in the vicinity of a PN junction when it is exposed to sunlight. As photons are absorbed, whole electron pair may be formed. If this mobile charge carrier reaches the vicinity of the junction, the electrical field in the depletion region will push the holes into the p side and push the electron in the n side, as shown in the upper left diagram, such that over here, the p side accumulates holes and the n side accumulates the electrons, which creates a voltage that can be used to deliver current to a load. If electrical contacts are attached to the top and bottom of the cell, electrons will flow out of the N side into the connecting wire through the load and back to the P side as shown in the bottom diagram. Since wire cannot conduct holes, it is only the electron that actually move around the circuit. When they reach the P side, they recombine with holes, completing the circuit. By convention, positive current flows in the direction opposite to the electron flow. So, the current arrow in the figure shows current going from the P side to the load and back to the N side. A simple equivalent circuit model for a photovoltaic cell consists of a real diode in parallel with an ideal current source as shown in this diagram. The ideal current source delivers current in proportion to the solar flux to which it is exposed. There are two conditions of particular interest for the actual PV and for its equivalent circuit. They are the current that flows when the terminals are shorted together, means the short circuit current ISH will flow, such as shown in this diagram over here, and the voltage across the terminal when the lead are left open, that is called the open circuit voltage, which is abbreviated as VOC. When the leads of equivalent circuit for the PV cells are shorted together, no current flows in the real diode. Since Vd is 0, so all the current from the ideal source flows through the shorted lead. Since that short circuit current must equal ISH, the magnitude of the ideal current source itself must be equal to the ISH, means short circuit current. Now we can write a voltage and current equation for the equivalent circuit of the PV cell as shown over here. To start with, I is equal to ISH minus ID, and then substitute the diode current equation by Shockley equation. It is interesting to note that the second term is just the diode equation with the negative sign, such as this one. That means that the response is just I short circuit current added to the diode curve turning upside down, as shown in this diagram. The diagram shows the current voltage relationship for a PV cell when it is dark, no illumination, and light when it is illuminated. So when the solar panels has no sunlight, the curve would be like this, and when it is facing the current sunlight, the curve will be upper one. When the leads from the PV cells are left open, the current I is equal to 0, and we can solve the current equation for the open circuit voltage VOC as defined over here. Short circuit current is directly proportional to solar insolation, which means that we can now quite easily plot sets of PV current voltage curves for varying sunlight. Also, quite often laboratory specifications for the performance of photovoltaics are given per centimeter square of junction area, in which case the current in the above equations are written as current density. Solve the exercise to understand the current and voltage relationship of a PV cell. There are times when a more complex PV equivalent circuit than the one shown in previous slides is needed. For example, consider the impact of shading on a string of cells wired in series as shown in the upper diagram, such as over here. If any cells in the string is in the dark, it produces no current. In our simplified equivalent circuit for the shaded cell, the current through the cell's current source is zero and its diode is back biased, so it does not pass any current either, other than the tiny amount of reverse saturation current. This means that the simple equivalent circuit suggests that no power will be delivered to a load if any of its cells are shaded. While it is true that PV modules are very sensitive to shading, the situation is not quite as bad as that. So we need a more complex model if we are going to be able to deal with realistic such as the shading problem. The bottom diagram shows a PV equivalent circuit that includes some parallel leakage resistance Rp. The ideal current source, the short circuit current, in this case, delivered current to the diode, the parallel resistance, and the load. The equation would become I is equal to I short circuit current minus ID minus the voltage divided by Rp. The first two terms in the current equation is the same current that we had for the simple model. So, what this new current equation tells us that at any given voltage, the parallel leakage resistance causes load current for the ideal model to be decreased by V divided by Rp, as is shown in I voltage current curve. This part. For a cell to have losses of less than 1% due to its parallel resistance Rp should be greater than about 100 times open circuit voltage divided by the short circuit current. For a large cells, the short circuit current might be around 7 ampere and open voltage might be about 0.6 volts, which says its parallel resistance should be greater than about 9 ohm. An even better equivalent circuit will include series resistance as well as parallel resistance. Before we can develop that model, consider bottom right diagram, this one, in which the original PV equivalent circuit has been modified to just include some series resistance Rs. Some of this might be contact resistance associated with the bond between the cells and its wire leads, and some might be due to the resistance of a semiconductor itself. The equation gives here can be interpreted as the original PVI voltage curve with the voltage at any given current shifted to the left by V is equal to IRS as shown in characteristic diagram. So this curve will be shifted toward in this direction left side and it will look like this. For a cell to have less than 1% losses due to the series resistance, Rs will need to be less than about 0.01 times the ratio of open circuit voltage to the short circuit current. For a large cell with short circuit current of 7 ampere, an open circuit voltage of 0.6 volt would be less than 0.0009 ohm. Finally, let us generalize the PV equivalent circuit by including both series and parallel resistance as shown in this diagram. We can write the equation for current and voltage as mentioned above. Unfortunately, this is a complex equation for which there is no explicit solution for either voltage V or the current I. Our spreadsheet solution, however, is fairly straightforward and has the extra advantage of enabling a graph of I versus V to be obtained easily. The approach is based on incrementing values of diode voltage VD in the spreadsheet. For each value of VD, corresponding values of current I and voltage output voltage V can easily be found. In conclusion, series and parallel resistance in the PV equivalent circuit decrease both voltage and current delivered. To improve cell performance, high RP and low RS are needed. To understand the equivalent circuit of a PV cell, plot IV characteristic and draw equivalent circuit diagram with Rs is equal to 0.05 ohm and Rp is equal to 1 ohm. Since an individual cell produces only about zero point 0.5 volts, it is a rare application for which just a single cell is of any use. Instead, the basic building block for PV application is a module consisting of a number of pre-wired cells in series, all encased in tough weather resistance package. A typical module has 36 cells in series and is often designated as a 12-volt module even though it is capable of delivering much higher voltage than that. Some 12-volt modules have only 33 cells, which be desirable in certain very simple battery charging systems. Larger 72 cell modules are now quite common, some of which have all of the cells wired in series, in which case they are referred to as 24-volt modules. Some 72 cells modules can be field wired to act either as 24 module with all 72 cells in series or as 12-volt module with two parallel strings having 36 series cells in each. Multiple modules in turn can be wired in series to increase voltage and in parallel to increase current, the product of which is power. An important element in PV system design is deciding how many modules should be connected in series and how many in parallel to deliver whatever energy is needed. Some combination of modules are referred to as an array. When photovoltaics are wired in series, they all carry the same current, and at any given current, their voltage add as shown in this diagram. That means we can continue the spreadsheet solution as practiced before to find an overall module voltage by multiplying terminal voltage equation by the number of cells in the module. To practice, determine the voltage and current from a PV module having 36 identical cells using spreadsheet method to determine the IV characteristic. Modules can be wired in series to increase voltages and in parallel to increase current. Arrays are made up of some combination of series and parallel modules to increase power. For module in series, the IV curves are simply added along the voltage axis, that is, at any given current which flows through each of the module. The total voltage is just the sum of the individual module voltage. For modules in parallel, the same voltage is across each module and the total current is the sum of the current. That is, at any given voltage, the IV curves of the parallel combination is just the sum of individual module current at that voltage. The diagram shows the current voltage curve for three modules in parallel. When high power is needed, the array will usually consist of a combination of series and parallel modules, for which the total current voltage curve is the sum of the individual voltage or individual modules IV curves. There are two ways of imagining wiring a series parallel combination of modules. The series modules may be wired as string and the string wired in parallel, or the parallel module may be wired together first and those units combined in series. You can see the difference between two strategy in these two diagrams. So in diagram A, there are two strings and each strings the modules are in series. And in the diagram B, so both of the top panels your modules are in parallel first and then connected in series to the other set of the parallel modules. The total current voltage curve is just the sum of individual modules curve, which is the same in either case when everything is working right. There is a reason, however, to prefer the wiring of the string in parallel. So this topology is preferable because if an entire string is removed from services, for some reason the array can still deliver whatever voltage is needed by the load, though the current is diminished, which is not the case when the parallel group of a module is removed. Consider the moment a single PV module that you want to connect to some sort of a load. The load might be a DC motor driving a pump or it might be a battery. For example, before, before the load is connected, the module sitting in the sun will produce an open circuit voltage, but no current will flow. If the terminals of the module are shorted together, the short circuit current will flow, but the output voltage will be zero. In both cases, since power is the product of current and voltage, no power is delivered by the module and no power is received by the load. So we have two extreme points in the graph. When the load is actually connected, some combination of current and voltage will result and power will be delivered. To figure out how much power, we have to consider the current voltage characteristic curve of the module as well as the current voltage characteristic curve of the load. The diagram shows a generic current and voltage curve for a PV module, identifying several key parameters including the open circuit voltage and the short circuit current. Also shown is the product of voltage and current, that is, power delivered by the module. At the two ends of the characteristic curve, the output power is zero, since either current or voltage is zero at those points. The maximum power point, abbreviated as MPP, is that spot near the knee of the characteristic curve at which the product of current and voltage reaches its maximum. The voltage and current at the MPP are sometimes designated as VM and IM for the general cases and designated VR and IR for rated voltage and rated current under the special circumstances that correspond to idealized test condition. Another way to visualize the location of maximum power point is by imagining trying to find the biggest possible rectangle that will fit beneath the characteristic curve, as shown in the diagram. The sides of the rectangle correspond to the current and voltage, so its area is power. Another quantity that is often used to characterize the module performance is the fill factor, abbreviated as FF. The fill factor is the ratio of the power at the maximum power point to the product of open circuit voltage and the short circuit current. So FF can be visualized as the ratio of two rectangular areas. Fill factors around 70 to 75% for crystalline silicon solar modules are typical, while for multi-junction amorphous Si module, it is closer to 50 to 60%. Since PV characteristic curves shift all around as the amount of insulation changes and as the temperature of cells varies, the standard test condition, abbreviated as STC, have been established to enable fair comparison of one module to another. Those test conditions include a solar radiance of 1 kilowatt per meter square corresponding to an air mass ratio of 1.5. The standard cell temperature for testing purpose is 25 degrees Celsius. It is important to note that 25 degrees Celsius is the cell's temperature, not ambient temperature. Manufacturers always provide performance data under these operating conditions. Manufacturer will often provide characteristic curve that shows how the curve shifts as insulation and cell temperature changes as shown in the diagram. Notice as insulation drops, short circuit current drops in direct proportion. Cutting insulation in half, for example, drops short circuit by half. Decreasing insulation also reduces open circuit voltage, but it does so follow a algorithmic relationship that result in the relative modest change in the open circuit voltage. Note that the insolation means here the radiance of the sunlight. As can be seen in the diagram, as cell temperature increases, the open circuit voltage decreases substantially while the short circuit current increases only slightly. Photovoltaic systems therefore perform better on cold, clear days than a hot one. For crystalline silicon cells, open circuit voltage drops by about 0.37% for each degree Celsius increase in temperature, and the short circuit current increases by approximately 0.05%. The net result when cells heat up is the MPP slides slightly upward and toward the left with a decrease in the maximum power available of about 0.5% per degree Celsius. Given this significant shift in performance as cell temperature changes, it should be quite apparent that temperature needs to be included in any estimate of module performance. Cells varies in temperature not only because ambient temperature changes, but also because insulation on the cell changes. Since only a small fraction of the insulation heating a module is converted to electricity and carried away, most of that incident energy is absorbed and converted to heat. To help system designer account for change in cell performance with temperature, manufacturers often provide an indicator called the NOCT, which stands for nominal operating cell temperature. The NOCT is cell temperature in a module when ambient is 20 degrees Celsius. Solar radiance is zero point 0.8 kilowatt per meter square and the wind speed is 1 meter per second. To account for another ambient condition, the following expression may be used. This one, where T cell is the cell temperature in degrees in cells centigrade, Tm is the ambient temperature, and S is the solar insolation in kilowatt per meter square. Solve the given exercise to understand the temperature effect on the PV characteristic. The output of a PV module can be reduced dramatically when even a small portion of it is shaded. Unless special efforts are made to compensate for shade problem, even a single shaded cell in a long string of cells can easily cut output power by more than half. External diodes purposely added by the PV manufacturer or by the system designer can help preserve the performance of PV module. The main purpose of such diode is to mitigate the impact of shading on PV characteristic curve. Such diodes are usually added in parallel with modules or blocks of cells within a module. To help understand this important shading phenomena, consider the systems as shown in which an N cell module with current I and the output voltage V shows one cell separated from the other, such as shown over here in these two diagrams. The equivalent circuit of the top cell have been drawn in detail as discussed previously, while the other n-1 cells in the strings are shown as just a module with current I and output voltage V n-1. In figure A, all of the cells are in the sun, and since they are in series, the same current I flow through each of them. In figure B, however, the top cell is shaded and its current source IS, ISC has been reduced to 0. The voltage drop across RP as current flows through it causes the diode to be reverse biased. So the diode current is also essentially 0. That means the entire current flowing through the module must travel through both RP and RS in the shaded cell on its way to the load. That means the top cell, instead of adding to the output voltage, actually reduce it. Consider the case when the bottom n-1 cells still have full sun and still somehow carries their original current I. So they will still produce their original voltage, which is V n-1, this one. This means that the output voltage of the entire module VSH, this one, with one cell shaded will drop to V n-1 minus the current that is flowing times Rp plus Rs. So this is the voltage drop within the shaded cell. With all n cells in the sun and carrying I, the output voltage was V. So the voltage of the bottom n-1 cells will be the V n-1, which would be n-1 divided by n times the voltage of the V of the terminal when all the cells are in the sun. The drop in the voltage at any given current I caused by the shaded cell is given by V minus VSH, which is abbreviated as delta V. Since the parallel resistance Rp is so much greater than the series resistance Rs, equation is simplified to this. So delta V is approximately equal to the voltage divided by N plus the current that is supplied by the module times the Rp. So using this equation, we can calculate how much voltage is being reduced due to one cell is shaded. The figure shows such curves of shading effect, for example, module under full sun condition and with one cell 50% shaded. So this is the curve when the module is in full sun, and this is the curve when one cell is 50% shaded. Also, it is shown on the graph is a dashed vertical line at 13 volt, which is a typical operating voltage for a module charging a 12-volt battery. The reduction in charging current for even modest amount of shading is severe. So you can see that if we have the shading of 50%, the current has reduced from 3.5 ampere to about 2.6 or 2.7. And if we have one cell completely 100% shaded, then we will have the volt current about 1.2 or 1.3 amperes. The reduction in the charging current for even modest amount of shading is severe, with just one cell shaded out of 36 in the module. The power delivered to the battery is decreased by about two-thirds. A solar cell in full sun operating in its normal range contributes about 0. 0.5 volt to the voltage output of the module. But in the equivalent circuit, a shaded cell experiences a drop as current is diverted through the parallel and series resistance. This drop can be considerable. The voltage drop problem in shaded cell could be corrected by adding a bypass diode across each cell. When a solar cell is in the sun, there is a voltage rise across the cell, so the bypass diode is cut off and no current flow through it. It is as if the diode is not even there. When the solar cell is shaded, however, the drop that would occur if the cell conducted any current would turn on the bypass diode, diverting the current flowing through that diode. The bypass diode, when it conducts, drop about 0.6 volts. So the bypass diode controls the voltage drop across the shaded cell, limiting it to a relatively modest 0.6 volt instead of the rather larger drop that may occur without it. In real modules, it would be impractical to add bypass diodes across each solar cells, but manufacturers often do provide at least one bypass diode around a module to help protect arrays, and sometimes several such diodes around group of cells within a module. These diodes don't have much impact on the shading problem of a single module, but they can be very important when a number of modules are connected in series. Just as cells are wired in series to increase module voltage, module can be wired in series to increase array voltage. Also, just as single cells can drag down the current within the module, a few shaded cells in a single module can drag down the current delivered by the entire string in an array. The benefit already demonstrated for a bypass diode on a single cell also applies to a diode applied across the complete module. PV system applications are of two types: standalone, that is independent equipment, and the system integrated with utility electricity grid. The diagram shows the typical configuration of a standalone application of PV system. Standalone system generally includes solar charging modules, storage batteries, and controls or regulators. Ground or roof mounted system will require a mounting structure, and if AC power is desired, an inverter is also required. In many standalone PV system, batteries are used for energy storage, as they may account for up to 40% of overall standalone PV system cost over its lifetime. These batteries cause losses in the PV system due to limited availability of time and energy to recharge the battery, in addition to the insufficient battery maintenance. Hence, a charge controller is then used to control the system and prevent the battery from overcharging and over discharging. Overcharging shortens the battery life, while undercharging may lead to sulfation and starification, which result in the reduction in battery effectiveness and lifetime. Batteries are often used in PV systems for storing energy produced by the PV arrays during daytime and supplying it to electrical loads as needed. Moreover, batteries are also needed in the tracker systems to operate at MPP in order to provide electrical loads with stable voltage. Nearly most of the batteries used in PV systems are deep cycle lead acid batteries. To extend battery lifetime and for efficient system operation, a charge controller is needed to regulate the flow of electricity from the PV module to the battery and the load. The controller keeps the battery fully charged without overcharging it. Many controllers have the ability to sense the excess of electricity drawn from battery to the load and stop the flow until sufficient charge is restored to the batteries. The latter can greatly extend the battery lifetime. However, controllers in standalone photovoltaic systems are more complex devices that depend on battery state of charge, which in turn depends on many factors and is difficult to measure. The controller must be sized to handle the maximum current produced. Several characteristics should be considered before selecting a controller, such as adjustable set points, including high voltage and low voltage disconnects, temperature compensation, low voltage warning, and reverse current protection. Moreover, the controller should ensure that no current flows from the battery to the array at night. Grid-connected photovoltaic systems are composed of PV arrays connected to the grid through a power conditioning unit and are designed to operate in parallel with the electrical utilities. The power conditioning unit may include the MPPT, the inverter, the grid interface, as well as the control system needed for sufficient system performance. There are two general types of electrical design for PV power systems: systems that interact with the utility power grid and have no battery backup capability, and systems that interact and include battery backup as well as shown in this diagram. The latter type of system incorporates energy storage in the form of battery to keep critical loads circuits operating during the utility outage. When an outage occurs, the unit disconnects from the utility and power specific circuit of the load. If the outage occurs in daylight, the PV array is able to assist the load in supplying the loads. The major component in both systems is the DC-AC inverter, or also called the power conditioning unit. The inverter is the key to the successful operation of the system, but it is also the most complex hardware. For household application, PV panels integration with uninterrupted power supply, abbreviated as UPS, system could be a simple and straightforward solution. There are three main configurations. Firstly, interconnecting PV with DC-AC inverter. The overall efficiency of the power system is low because of four power conversion stages from PV array to the load. In a typical grid-connected PV inverters, a DC-DC converters and a DC-AC converters are connected in cascaded. In this topology, there are additional two power conversion stages inside a UPS. Typical weighted efficiency for commercial grid-connected PV inverter is about 96 to 97%. For external cabling and connections, about 1% losses should be estimated. As a result, approximately 91 to 92% total power conversion efficiency for the PV system can be achieved with this topology. Another disadvantage in this topology is the space occupied by the separate PV inverters. Also, additional cabling and connection between separate units are increasing total system losses. Alternative solutions to integrate PV source and a UPS is to replace inverter with a DC-DC converter and connect it directly to the DC bus inside the UPS device, such as over here. Compared to previous topology, there are two power conversion stages less in this topology. meaning higher total system efficiency. This topology also provides the possibility to integrate the PV interface into the same hardware platform with the UPS and energy storage. Reducing power cabling and connection improves also total system efficiency. Typical efficiency for the DC-DC converter in the PV interface can be as high as 98 to 99%, and it can be integrated both electrically and mechanically directly to the DC link of the UPS. Efficiency of the DC-AC conversion inside a UPS can be higher than 98%. For external cabling and connection, less than 1% losses can be estimated. As a result, approximately 96 to 97% total power conversion efficiency for the PV system can be achieved with this topology. The third topology alternative is to connect PV array directly to the DC bus of the UPS. In this topology, there is only one DC-AC power conversion stage from PV source to the load. Theoretically, highest possible total power conversion efficiency, about 97 to 98%, could be reached with this solution. Also, integration rate and power density of the system would be highest. However, some drawbacks are related to this solution. The DC bus voltage of the UPS is regulated and voltage level has to be kept in the certain limit in order to perform its basic operation as a UPS device. In this topology, PV array voltage should be specified to, the, to that same narrow voltage range. PV panel is inherently a nonlinear current source, and its output power is dependent on ambient temperature and radiation. Based on that, there would be only few operating points in occasion when the PV source was able to generate power to the load. This means that we cannot achieve the maximum power point in this topology easily. In today's lecture, we have discussed about the application of photovoltaic system and its photovoltaic cells and the integration of PV system with the grid. Today's lectures end here. Thank you for listening.